Good morning to all of you. In previous session, we have seen direct form and cascade realization structures for FIR systems. Today, we'll discuss lattice structures which can be used to realize FIR systems, as well as we see how to convert lattice structure coefficients to direct form filter coefficients or direct form discrete time system coefficient. So the lattice structure the lattice structure can be represented in single stage, two stage, or three stage, depending on what is the order of given system function, right, or the given input output function. So just for example, if there is an input output relationship given as y of n is equals to x of n plus alpha 1 of 1 x of n minus 1. So it is the first order difference equation. This can be represented in system function form as well, okay, by taking its z transform. So this is the direct form realization equation, okay. So this alpha 1 of 1 is the direct form coefficient, okay. So it is the direct form filter coefficient, and this can also be represented in h of z form, that is system function form, by taking its z transform. So its z transform will be y of z is equals to x of z plus alpha 1 of 1 z inverse x of z, right? So you can take x of z common, and this will be y of z upon x of z is equals to what you will have. So it will be 1 plus alpha 1 of 1 z inverse, okay. This is nothing but the h of z, okay. So you can use this for direct form realization. So this is FIR system, you can realize it by using direct form realization. How you can realize it? So again, x of n or x of z, right, is there, and here you can add this one, right. You can draw it horizontally or vertically, right. So I'm drawing it horizontally, so one will be added here, right. It will be added with this delay, and which is multiplied by a constant, that is alpha 1 of 1. This is output, that is y of n or capital Y of z, okay. So this is how you can realize this direct form one realization of the given input output equation, right. So in case of lattice structure, this direct form equation can be represented as input x of n, right. So it can be realized by using single stage lattice structure, where we will be using two adders, then one delay element, that is z inverse, okay. Again, adder will be there, and we'll be utilizing this lattice structure coefficient, which is nothing but k1, okay, for single stage lattice structure, okay. Here you can have this output y of n, here this single stage lattice structure of is g1 of n, okay. So here you can also represent these intermediate values as this x of n is going as f0 of n. In this case, the single stage output is represented as f1 of n, okay, which is nothing but simply y of n. Here this input can be represented as g0 of n, which is then delayed to get g0 of n minus 1 here, right? And output here will be represented g1 of n. So basically from this direct form equation, and by utilizing this direct form coefficient, you can identify this lattice structure coefficient, that is k1. Okay, so this figure indicates the single stage lattice structure. Okay, you can even write down these equations as which are represented here, this f0 of n, which is nothing but this g0 of n, which is nothing but your x of n. Okay, in this case, this f1 of n, okay, equation for f1 of n, that is nothing but y of n, is simply this f0 of n is coming as it is. Okay, so f0 of n plus this k1 is getting multiplied with g0 of n minus 1. So k1 g0 of n minus 1. So this f0 of n is nothing but x of n plus k1 g0 of n minus 1 is nothing but x of n minus 1. So this is equation for this y of n or f1 of n, right? Similarly, the equation for this g1 of n is equals to this f0 of n multiplied by k1. Okay, this is k1 f0 of n. This is added with g0 of n minus 1. g0 of n minus 1. Okay, so this is nothing but k1 x of n plus x of n minus 1. Okay, so these are for single stage lattice structure or lattice filter, right? So similarly, you can draw it for the two-stage lattice structure. Only this direct form equation can be written as for this two-stage lattice structure x1 x of n plus, in place of alpha 1 of 1, it will be alpha 2 of 1. Alpha 2 of 1. Basically, here the coefficient is there, that is alpha 2 of 0, right? Alpha 2 of 0 is 1 in this case, right? As well as here the coefficient of x of 1, alpha 1 of 0 is there, but alpha 1 of 0 is 1 in this case, right? So alpha 2 of 1 into x of n minus 1 plus alpha 2 of 2 x of n minus 2 will be there. For this also you can draw the two-stage lattice structure as x of n. Again, you have an adder, delay element that will be there. Again, an adder, delay element, and adder. Okay. So this is nothing but your two-stage lattice structure. Again, you can indicate it as g2 of n. So this will be your y of n, which is nothing but f2 of n. Right here in first stage, the lattice structure coefficient will be k1, right? Here in second stage, the lattice structure coefficient can be denoted as k2. Okay. So 4 adders are there, and these 4 constant multipliers and 2 delay elements are there, right? Again, you can write down is intermediate uh, inputs here. So this can be f0 of n, g0 of n. Here you can represent it g1 of n. Here it will be f1 of n, right? So this is how you can represent the two-stage lattice structure. Okay. So this figure indicates two-stage lattice structure. So these values of k1 and k2 can be identified by using this direct form equation and by utilizing this direct form filter coefficient, that is alpha 2 of 0, alpha 2 of 1, alpha 2 of 2, right? So again, this equation can be converted into system function h of z by taking its z transform, right? You can obtain this h of z and then you can realize it by using this direct form realization, right? As we have obtained it here, right? So we did it here for single stage or first order difference equation. Similar sort of realization you can obtain, that is direct form realization you can obtain for this second order equation, right, by obtaining its system function. Okay, so you can try it at your own end, as well as you can try to identify the equations here, right, that is y of n and g2 of n equations. What do you have obtained here for y of n and g1 of n, right? So let's see how to convert these lattice coefficients to direct form filter coefficient. So now we'll discuss conversion of lattice coefficients to direct form filter coefficients. Okay, so the direct form FIR filter coefficients can be denoted as alpha m of k. Okay, whatever we are saying here, that is, here three coefficients were there, that is alpha 2 of 0, alpha 2 of 1, alpha 2 of 2. Here it is alpha 1 of 0 and alpha 1 of 1, two coefficients there. So this direct form filter coefficient, this alpha m of k, represent the direct form FIR filter coefficient or FIR system coefficient. Okay, so this alpha m of k can be obtained from the lattice coefficients. So these lattice coefficients can be represented as ki. Okay, in two-stage lattice structure, those coefficients were k1, k2, while in single stage lattice structure coefficient is k1. In three-stage lattice structure, coefficients will be k1, k2, k3. So this ki indicates the lattice coefficients, lattice structure coefficients. Okay, so for obtaining these direct form coefficients from lattice coefficients, you can use this equation as a0 of z is equals to b0 of z is equals to 1, right? So this a0 of z is nothing but the given equation or system function, right? And from this a0 of z, you can identify a1 of z or am of z. That is, a1 of z will be equals to a0 of z, am minus 1 of z. A0 of z is nothing but am minus 1 of z plus km z inverse bm minus 1 of z. And for obtaining this bm minus 1 of z, you can use z to the power minus m am z inverse. Okay, and here these values of m will be, m is equals to 1 to capital M minus 1, right? Similarly here also m is 1 to capital M minus 1, right? So the solution here is obtained recursively beginning with m is equals to 1, right? So you will have equation a1 of z is equals to a0 of z plus k1 z inverse b0 of z. Okay, so this b0 of z you can obtain from z inverse a1 of z inverse, right? Here it should be bm of z. Okay, not bm minus 1 of z. Okay, so you can use this equation, that is a0 of z is equals to b0 of z is equals to 1, am of z is equals to am minus 1 of z plus km z inverse bm minus 1 of z. Bm can be obtained as z to the power minus m am z inverse. Okay, so let's see an example where the lattice coefficients will be provided. From this lattice coefficient we'll try to obtain these direct form filter coefficients. Okay, so here you can see in this example these lattice coefficient k1 k2 k3 are given, right? So the lattice coefficients are k1 is equals to 1 by 4, k2 is equals to 1 by 2, and k3 is equals to 1 by 3. So you can obtain the lattice structure here. In solution there is no need to obtain the lattice structure, but only for your understanding I am just drawing here the lattice structure. So input will be x of n or x of z, you can indicate, right? So here you have delay element, then you have adder in first stage again, and adder, then delay element, and again adder will be there. Again you have an adder and delay element will be there. So output will be y of n or y of z will be there, right? This will be your g3 of n, right? And here you can indicate the coefficient, lattice coefficient. Okay, so the value of k1 in this case is 1 by 4, right? While k2 is 1 by 2, and k3 is 1 by 3. Okay, so this is nothing but the lattice structure realization by using these three lattice coefficient k1 k2 k3. Okay, so this is nothing but lattice structure realization. Okay, so now let's see how to convert this lattice coefficient into the direct form filter coefficient. Okay, so as per this equation, you have a0 of z and b0 of z is equals to 1. So you will start with a0 of z is equals to b0 is equals to 1, right? Then you can write the equation here, that is a1 of z is equals to a0 of z plus k1 z inverse b0 of z, right? Correct, because you have this am minus 1 of z is equals to, sorry, am of z is equals to am of z is equals to am minus 1 of z plus km z inverse bm minus 1 of z, right? So this equation I am writing here. So initially you will start with m is equals to 1, so you have equation a1 of z is equals to a0 of z, the value k1 will be there, right? Then z inverse and e0 of z will be there. So a1 of z is equals to, what is the value of a0 of z? 1, right? Value of k1 given in example is 1 by 4 z inverse, and b0 of z is again 1. So this is a1 of z, right? So here the coefficients of FR filter, that is direct form coefficient, here this alpha 1 of 0, okay, that is alpha 1 of 0 is 1, right, in this case, and alpha 1 of 1, alpha 1 of 1 is 1 by 4 in this case, right? So these two coefficients are there, correct? But you are interested in identifying the third order equation, right? Because it is a three-stage lattice structure. Okay, so now from a1 of z you can obtain b1 of z. So for obtaining b1 of z, your equation bm of z is equals to that bm of z is equals to z to the power minus m and am of z inverse, right? So b1 of z you can obtain as z to the power minus m, means z inverse will be there, right? And am of z inverse will be simply your 1 plus 1 by 4 z, right? So if you multiply it with this z inverse, so you have this b1 of z. So b1 of z will be this z inverse will be there, right? Plus 1 by 4 z into z inverse will be simply 1 by 4. So I'll write it as 1 by 4 plus z inverse, right? Now similarly for this is we have obtained for m is equals to 1, right? Similarly for m is equals to 2, you can have this equation written as a2 of z plus a1 of z plus k2 z inverse b1 of z, right? So a2 of z is equals to a1 of z plus k2 z inverse b1 of z will be there. So a2 of z is equals to, what is the value of a1 of z? So 1 plus 1 by 4 z inverse. So 1 plus 1 by 4 z inverse plus, what is the value of k2? K2 is 1 by 2 given in example. So it is 1 by 2 in bracket z inverse bracket, what is the value of b1 of z? So b1 of z 1 by 4 plus z inverse 1 by 4 plus z inverse is there. Right, so if you simplify it, so a2 of z is equals to 1 plus 1 by 4 z inverse, right, plus, so if you multiply it, so it will be 1 by 2 z inverse multiplied by 1 by 4, so it will be 1 by 8 z inverse, right, again 1 by 2 z inverse multiplied by this z inverse, so it will be 1 by 2 z to the power minus 2. So a2 of z 1 plus this 1 by 4 z inverse plus 1 by 8 z inverse. Okay, so it will be 3 by 8 z inverse, right, and this will be 1 by 2 z inverse as it is, right. So here the coefficients are from this a2 of z. You can write these coefficients as alpha 2 of 0 is 1, right, comma alpha 2 of 1 is 3 by 8, and alpha 2 of 2 is 1 by 2, right. These coefficients, three coefficients are there: 1, 3 by 8 and 1 by 2, right. So again from a2 of z you can obtain b2 of z, right. So again, as per this equation, b2 of z will be z to the power minus 2 a2 of z inverse, right, z to the power minus 2 a2 of z inverse will be there. So z to the power minus 2 a2 of z inverse will be 1 plus 3 by 8 z plus 1 by 2. Here it is z to the power minus 2. Okay, z to the power minus 2, not minus 2, it will be, as we have taken z inverse, so it will be z square, right. So if you multiply it with this z to the power minus 2, so you have b2 of z. So this b2 of z will be simply this z to the power minus 2 z square will be 1, right, so it will be 1 by 2 plus 3 by 8 z inverse will be there plus z to the power minus 2 will be there. This z to the power minus 2 multiplied by 1 z to the power minus 2 will be there. Okay, so from this you can obtain a3 for m is equals to 3. So what equation you have? a3 of z is equals to a2 of z plus k3 z inverse b2 of z, right. So a3 of z is equals to a2 of z plus k3 z inverse b2 of z. So we have this a2 of z 1 plus 3 by 8 z inverse plus 3 by 8 z inverse plus 1 by 2 z to the power minus 2, right, plus what is the value of k3? K3 is 1 by 3 in the given equation. In given example it is 1 by 3, then z inverse multiplied by this b2 of z, so it will be 1 by 2 z inverse, right, so 1 by 2 z inverse, then 3 by 8 z to the power minus 2 will be there. I'm just multiplying this z inverse inside bracket, and this z to the power minus 3 will be there. So again, if you simplify it, so a3 of z will be 1 plus 3 by 8 z inverse plus 1 by 2 z to the power minus 2 plus 1 by 6 z inverse plus 1 by 8 z to the power minus 2 plus 1 by 3 z to the power minus 3, right. So if you add these terms, so 1 plus this z inverse term, I will be adding, that is 3 by 8 z inverse plus 1 by 6 z inverse, so it will be 13 by 24 z inverse, and this 1 by 2 z to the power minus 2 plus 1 by 8 z to the power minus 2 is 5 by 8 z to the power minus 2, and the remaining 1 by 3 z to the power minus 3 will be as it is. So this is the last required equation. So the required direct form a fire system or filter coefficients are, so alpha 3 of 0 is 1, then alpha 3 of 1 is 13 by 24, then alpha 3 of 2 is 5 by 8, and alpha 3 of 3 is 1 by 3, right? So this is the required, so these are the required direct form filter coefficient. Okay, so this is how you can obtain the direct form fire filter coefficient from the lattice filter coefficient. Okay, even you can draw this direct form realization for this final equation. We have equation a3 of z is equals to what, 1 plus 13 by 24 z inverse plus 5 by 8 z to the power minus 2 plus 1 by 3 z to the power minus 3. Okay, so how you can draw it? So again, x of n or x of z will be the input. So here you can indicate as 1, here you can use delay element, then here you can use a constant multiplier for 13 by 24, and adder will be there, then another delay element, again a constant multiplier will record for this 5 by 8, this will be added here, again another delay element will be required, this last term. Okay. So again 1 by 3, this adder will be there, output will be y of n or y of z. Okay, so this is nothing but direct form realization. Okay, so in this example, basically what has been asked, we have to determine the fire filter coefficient for the direct form structure from this lattice structure coefficient. Okay, so there is no need to draw this lattice structure diagram, right? So this has been drawn only for your understanding purpose, right? Then by utilizing these equation a0 of z, b0 of z, am of z, and bm of z, we have recursively identified am of z and bm of z, and from am of z we identified the direct form filter coefficients, right? So the final required coefficients are these. Okay, again there is no need to draw this realization structure, again this has been drawn only for your understanding purpose. Okay, so these are the required direct form filter coefficients. So in next session we'll be discussing how to identify the lattice structure coefficients from the direct form filter coefficients. Okay, so that means alpha values will be given in the example, and from alpha values we have to identify the values of k ki's, that is k1, k2, and so on, depending on what is the order of the function or the system. So thank you for joining this session.